You probably don't know me much because I spend most of my time at the Caja Institute as part of the neural engineering lab. You probably have seen me wandering the hallways because I always lost them. But okay, so I'm going to start my PhD. I'm a second-year PhD student. My doctoral thesis is prepared by simulation to manage factor results. I will start with a brief introduction, motivation, and then kind of paper style content. So as for introduction, first the motivation. Why we want to research alternative methods to manage tremor in Parkinson's disease. As most of you know, Parkinson's disease is traditionally defined by four cardinal signs: rigidity, peritonitis, that is the slowness of movement, postural instability, and tremor. And we focus on the tremor component of the disease, which is the most prevalent symptom. It is estimated that affects between 79 and 90% of Parkinson's patients, and is the most bothersome. As for essential tremor, as the name implies, the main symptom is tremor. In this case, is postural tremor, which means that the patients only experience tremor when they are holding a position in less gravity, such as this one or this. In the case of Parkinson's disease, it's a resting tremor, which means they only have tremor when they are holding their hands against their legs. Usually it's like a money counting tremor. They like, I have a lot of money. And all the symptoms start, the first line treatment is medication. In the case of Parkinson's disease, the main objective is to increase the levels of dopamine, either increasing the dopamine or decreasing the substances that decrease that dopamine, with levodopa, dopamine agonists, and other inhibitors. For essential tremor, beta blockers, nerve-resistant depressants, or even botulinum toxin injections that you may probably know as Botox, are prescribed to reduce the tremor in symptoms. However, the medication is only a trade-off between symptom management and side effects. And as the disease progresses, the side effects start to pile up. When the medication is no longer effective or the side effects are too much to handle, secondary treatments come into play, namely neurotherapy. The objective is to act on the central oscillators of memory, which you can done either ablating certain brain structures with thermal ablation, gamma knife surgery, or MRI hypothesis, or with the brain stimulation, that they use a stimulator with a probe of the brain, and with high frequency electrical stimulation, they can inhibit certain brain structures. But as you probably have guessed, this has a lot of problems, such as infection, intracranial hemorrhage, paresthesias, and not everybody wants to have a neurosurgery, and also it's kind of expensive. So, in the past years, it has become really a topic that we have to find other options to treat tremor in a non-invasive, innocuous manner. So, peripheral electrical stimulation has arisen as this novel option, which is affordable, innocuous, is below motor threshold, which means it doesn't interfere with the voluntary movements, and it can be available to all patients because, for example, neurosurgery, when you are above 60, you are not a candidate for neurosurgery. So what do? We try to modulate the circuit of reciprocal inhibition, which you probably have seen in some way when when a doctor hits your knee and suddenly your knee extends, that is reciprocal inhibition. In this case, when a flexor is contracted, it's activated, the extensor must be inhibited to prevent it from working against the contraction. So if we flex our wrist, the extensor must be relaxed, so we don't like contract both of the nerves. And this is done via an afferent fiber. Afferent fibers are the ones in charge of sending the sensor information. And then this afferent fiber synapses with a motor neuron that controls this muscle, and at the same time, this afferent fiber synapses with an inhibitor interneuron that relaxes this muscle. So how we try to modulate this to reduce tremor. So, for example, we have a muscle that is releasing tremor, that is contracting. We stimulate antagonist muscle. This impulse travels to the spinal cord via this afferent fiber, relaxes this tremor muscle, and at the same time stimulates the muscle that was relaxed. So in this case, we try to reduce tremor by increasing the excitability of the antagonist motor neuron pool and decreasing the excitability of the electromagnetic motor neuron pool. Just for the sake of being technical, in the wrist, the circuit is not functional because the wrist muscles are not pure antagonists. They are antagonists in the case of flexion extension, but for example, in grasping, they are synergists, which means that they have the same function. So other fibers are involved in this circuit. So how do we try to modulate this? With the selective and adaptive timeless simulation algorithm. This is a case of Parkinson's patient and the corresponding electromyographic signal, which is the electric signal that we measure when the muscles are activated. So first, with the start, we start with a recording window, and as you can see, first the flexor is activated, then the extension, and so on. This is a perfectly auto-paced pattern. When one is activated, the other is relaxed, and vice versa. And the algorithm, once it detects that in this recording window there's tremor, it enables an stimulating. And with the stimulating window, we check again which muscle is activated. In this case, you can see how the tremor bars is beginning, and in this case, it corresponds to the flexor. Therefore, we stimulate the flexor, the antagonist muscle. And again, it will now the turn of the extensor activation, and we stimulate the antagonist, the flexor, and so on. So my thesis comes from a long way from a research line that has been in the group for many years. So what now? First is to analyze the long-term effect of the therapy, because so far we have only done like single sessions, and also to characterize the plastic changes, why this therapy produces a tremor reduction, and also a tremor reduction that sometimes is 24 hours lasting. And also, we want to check whether these changes are at the spinal level or a supraspinal level at the level of the brain. So from activities and methods, some of the neurophysiological assessments that we check to see if these changes are spinal or supraspinal. So first we use the Hoffman reflex, or simply the H reflex, which is the electrical equivalent to the hammer to the knee. In this case, instead of using a hammer, we use electrical stimulation to stimulate the same fibers that the hammer would stimulate mechanically. In this case, if we stimulate the nerve at low intensities, this signal traverses spinal cord, synapses with the motor neuron, and produces an H reflex in the EMG. Then, if we increase more the stimulation, we also stimulate, apart from the afferent fibers, directly the motor fibers. And we have a direct response, that is the motor wave, EM wave, and the previously mentioned H wave. But also, when we stimulate at these high intensities, we produce an antidromic volley, which means that goes in the other direction. Instead of going this way, it goes the other way, and collisions with the previously mentioned H wave. So the H wave keeps increasing until the antidromic volley happens. In this case, the H reflex will disappear and the M wave will keep growing. So we can use this pathway to measure the inhibition from one muscle to the other. In this case, we stimulate the agonist muscle and the antagonist muscle through the inhibitory neuron. So we stimulate only the agonist muscle and we produce the M wave and the H reflex. This is an unconditioned H reflex. And if we stimulate the antagonist nerve, we will inhibit this response through the inhibitory interneuron, and the H wave will reduce in amplitude. So we obtain these profiles of the EMG. Here we have the unconditioned H reflex, which has a greatest amplitude, peak to peak. And if we time the both stimuli to coincide at the spinal cord, we can inhibit activity. You can see how the amplitude is lower, and even we can almost leave it at none. And we calculate the inhibition for here. We can also modulate the ongoing EMG, which means that we will modulate the response that is corticospinal, which means that is the voluntary response. In this case, it's happening to a voluntary contraction. So with a voluntary contraction, we just have the input from the corticospinal voluntary impulse, and we obtain this EMG. And if we stimulate the antagonist nerve, we will have a lower amplitude of the EMG. And after rectifying the signal and more signal processing, we obtain the signal, and we can see here how there's a drop in the signal, and that is the inhibition. And also, in this case, to check the supraspinal plasticity, we use the somatosensory evoked potentials. In this case, we stimulate the median nerve pathway width and check on the pathways of the sensory, till the sensory cortex, which means all the sensory information that goes from the nerves, goes to spinal cord, and finally to the cortex. So we deliver an impulse, and with electrodes we check the different signals that we obtain at different points. And then we check the amplitude, and from this we can check the corticospinal cortical plasticity. As for results, well, we have tried this strategy with essential tremor and Parkinson's disease, and this is before stimulation and after stimulation, and 24 hours after delivering stimulation. And this is not a photo, this is a video of a Parkinson's disease patient after the therapy. So it's kind of nice that they without tremor. And regarding the plastic changes, we have done this study with healthy participants, and we have seen that out of this stimulation, which means that when the agonist activity we stimulate the antagonist, which is the one we use with the patients, reduces the inhibition, and the contrary pattern, which means that if the agonist is activated to stimulate the agonist, the same muscle, increases the inhibition. So our hypothesis is that there are spinal changes. As for discussion and conclusions, what's the supposed impact of this thesis? We want a non-invasive alternative to the classical interventions, either medication or neurosurgery. And we want to analyze also the mechanism involved in tremor. And in the end, we want to establish the peripheral electrical stimulation as a neuromodulatory technique that can be used in other diseases, such, for example, stroke or any disease that has spasticity, that in the end is a misbalance between excitatory and inhibitory input. And in the end, we want to make patients and their family happy. And that is all. Thank you for attention.
And now we have some minutes for discussions. If anyone wants to ask any question, just raise your hand.
Curiosity. Usually, I think talking about the neurosurgery, the word paresthesia. What is it?
Paresthesia means that they have kind of the tickles when you feel when one of your arms has sleep.
Yeah.
It's like a sensation that shouldn't be there.
I might have a question. Maybe I missed it, but I've seen the video with all the electrodes, and how you select specifically which nerve are you targeting? I mean, I suppose you apply an electric field. And...
we usually use the median, which is right here, and the radial nerve, that are responsible for the flexion and extension. It's because, as you can see here, the essential tremor is usually characterized by a flexion extension tremor. So we target the nerves that are responsible for the tremor. If it were, for example, Parkinson's disease is more complex because usually have a chronos of initiation tremor that moves like this, and those nerves are really difficult to stimulate because they are deeper in the arm. So first, we started with essential tremor, and then the patients that we have tried with Parkinson's disease are patients that have a typical flexion extension tremor, not the chronosupination or even the manicamting tremor.
I have one question also. Does this Parkinson's disease needs to be already happening for a long period of time, or is this therapy effective maybe if you attack it super early? Only when the therapy, only when the Parkinson's disease is located, no?
The thing is to stimulate, that's one of the problems we have. It usually works better with people that have high tremor because the algorithm is more robust when tremor is clearly present. So yes, it can be used when the Parkinson's disease is starting, but you have to have certain degree of tremor just to accurately stimulate the patient. Yeah, but our idea would be like, for example, in Parkinson's disease, that Parkinson's disease is more complex because it has also non-motor symptoms that in the end they appear later in the disease course, but they are the most bothersome for the patient also. So the idea would be like if you start with the motor symptoms with tremor, start with this therapy, so you can like later on the disease start with the medication that has all the side effects when you start to have these non-motor symptoms that obviously this therapy cannot manage.
Thank you.
And the idea of applying the therapy would be to apply it weekly, or how much do the effects last on the patients?
It depends on the patient. Some patients just have like an acute effect, like when I finish the therapy, I'm okay, and 24 hours I'm back to normal. But some patients have a 24-hour relief, and now we are starting with the long-term effect of the therapy, which and we see from the first patient that there's a decline on the tremor amplitudes throughout the day. So the ideal would be like you start your day, you apply 20 minutes of stimulation, and you can go on with your day with no tremor, and the next day you start again, and the next day, and throughout the week you should see a reduction of the tremor. But from one day to another, you should be able to live your life. Yes.
Thank you.
So do you and your group see this as something that could be treated with, for example, like an implant, or something that you need to?
Yeah, actually, this project, the STEM project, it was like a mix between application and technological impact. Like, for example, the other partners were the Universidad de Barcelona, and they developed an implant. Like the idea was, in this one, I don't think you can see it. Maybe, yes, this one is, well, it was an implant that it was that you introduce in the muscle. And the idea was to introduce these electrodes and just leave them there. And they are capable of both recording signal and stimulating signal. So the idea, they have volume conduction, powered by volume conduction. So it's just 2 bracelets and the implanted electrodes. And with that, it's powered over volume conduction. So you just put them there and you can live your life, and you don't have no batteries, no whatsoever. And the idea was that you just implant them and you, okay, I want to do my 20-minute session therapy. I put on the bracelets, they are powered, you start like that. Okay, now I'm fine. And the implants stay there, and the next day again. So the idea was that, but you can see that implanting electrodes in your body, some people may not want that. So maybe our idea as a future is like a textile implant, like the basketball players that have a sleeve or something like that. Because as you can see here, is kind of cumbersome on the setup.
First of all, thanks for the talk. It was super cool and interesting topic. And just a quick one: have you planned on, studying any kind of long-term improvements?
Studying long-term improvement, yes, it's what we are currently doing right now. We started with maybe thinking about a 4-week therapy, but patients are not so keen on going to the hospital every afternoon for 4 weeks. And now we are just going with 2 weeks, and yes, we have seen so far improvement.
And what's the perspective?
We will see, but we think that if we, with one session, some patients just go home and 24 hours after they are better. With the patients we have seen so far, as the time goes on, each day is better and better and better. But we think that, I don't know, this patient, for example, at week 2, there's a plateau that no more treatment is going to reduce more the tremor. I don't know if I answered your question.
Yeah.
If there's no more questions, we will move to the next speaker. Thank you.
Second speaker that we have today is a speaker who has already a lot of experience in voicing talks, and again now he's starting this session. So this speaker is Pablo de la Rosa del Val. Pablo, who's sitting here. Pablo finished his bachelor thesis in telecommunications here at UPM, and then his master's in photonics engineering at Universidad Carlos III de Madrid. I hope I told that right. But when he was doing his bachelor's and master's, he did both his practical parts of his thesis at Sendatic here, the institute here, and he's now pursuing his PhD again in liquid crystals in applied electromagnetism group of intelligent reconfigurable surfaces based on liquid crystals. I couldn't believe this. So we can give a warm welcome to Pablo again.
Okay, my presentation is not going to be as pretty as the one before. I'm sorry, graphic design is not my passion. Well, and I'm going to talk, all the weird words, it's what they use in the literature to name reflector arrays antennas, or, well, based on liquid crystals. And I'm going to talk both about the liquid crystal part and about the reflector array part. Starting with the reflector arrays, there's two parts to the word. The reflect part, which means it's reflected devices. So we have an incoming wave, electromagnetic wave, but we can also see with light, which with a normal surface, ground plane in a way, a mirror in a way, just reflects our incoming wave. The array part means that we have a matrix-like structure where we have an array or a matrix of similar elements, which we typically call unit cells. So we have this repeated pattern of many small unit cells that create our array. Going a bit more into this, as I briefly mentioned before, when we have a ground plane or when we have a mirror, our reflection of our incoming wave is specular. This means it has the same angle of incidence as the angle of reflection. But ideally, since we are developing something, we don't want just that specular reflection, but rather we want to be able to control at what angle we are reflecting our wave. A typical thing that does this, not in reflection, but in transmission, are prisms. Prisms, depending on the angle that the prism has or redirected the incoming light into a certain output angle, which in a way, though through transmission, it's similar to what we want to do here. An approximation to prisms would be a specific phase pattern where we have different phase steps. This is discretizing the prism, but we could approximate them through having small steps of different phase delays, which in itself create this pattern of the redirected wave that is transmitted. This we can obviously do with our arrays. If we manage to create stripes of these different phase delays, where we introduce a different phase delay to each of the lines, we in a way reproduce what the prism does. We are able to redirect whatever incoming wave we have towards a different direction. Again, conceptualizing this as in transmission, but in reflection, we can do something similar. But how do we do this? Because if we start just with our matrix and we put nothing in that matrix, we have a ground plane in a way. And the ground plane, as we said before, only has the specular reflection. So this wouldn't specifically work. So we need something that does something that interacts in a way with our incoming wave, and so that the reflection has an introduced phase. And we have to be able to tune the phase because, again, we want to achieve different phase delays within our structure so that we're able to generate that prism-like situation. So we're going to have to dive a bit deeper into what do we need. And what do we need? It's the typical thing we use is resonance structures. Resonance structures use resonances within the electromagnetic field to achieve this phase delay. Going a bit into resonances, it's something inherent to oscillatory systems, which through using an external force, so using an external source of interaction at the exact same frequency of the natural frequency of the system, create a resonance. Natural frequency of the system, you might know, no matter if it's electromagnetic or other kind of resonances, is the frequency at which an oscillation is kept in absence of any disturbance. This means no losses, no extra energy put into the system. So an example of this is a dipole where with an applied electromagnetic field, so with an external force applied, we create a movement of charges that if the applied electromagnetic field is at a frequency such related to the natural frequency of our dipoles, we create a resonance. As we're using an external force, this means since we have losses in the real world, this means we have an absorption. This absorption tends to be a peak of absorption, and depending on the quality factor of the resonance, which is a specific factor that we don't go very deep in, that resonance has a higher absorption. Well, this is the reflection coefficient, so what we would reflect has a higher absorption ratio. And something very relevant to the resonances is that they have abrupt phase changes. This means that with this abrupt phase changes, we're able, if we can tune where we have these resonances, we're able to achieve whatever phase delay we want to do. How do we do this? Or what is related to, or how do we vary where the resonance is? Well, since we can vary the natural resonance frequency of our devices changing its geometry, for example, so we change a bit the geometry, and we're able to slightly shift where our resonances are. So, for example, changing geometrically our devices, we achieve moving in a way. Here's a small slide where we have changing dimensional parameters. So, for example, the length of our dipole, and with different frequencies, we see that there's a shift on the phase where the phase delay happens, where the resonance is. This would, in a way, imply where these peaks are. So with this, knowing that, for example, at a specific frequency at 9 gigahertz, which is the red one, by changing the size of our dipole, we can change the phase delay level we can achieve. This means that just by changing our sizes along a certain direction, we would achieve, in a way, a prism, which is what is shown here. But there's another catch, which is where the other part of our talk comes, which the natural frequency of our system also depends on the materials we're using. So if we change the materials we're using, or more specifically, because we work with this in electromagnetic systems, if we change the permittivity of our material, we're able to also shift where our resonances are. And this is shown here where, again, we have different permittivities, and at different frequencies, we see that we change where the resonance point is, and we also change the phase that we have. So we have a material that we can select its permittivity. For the people that maybe know more about optics, if we have a material that changes its refractive index, we're able to, again, tune where we have the frequency and thus achieve the same prism-like situation. So now going into liquid crystals, which is the other part of the talk, and it's actually where I come from a bit. Liquid crystals are a state of matter intermediate in between liquid and solid crystallines, where there's a high orientational order. So as we can see here, all molecules within this type of material, or this organization of material, align in a similar direction, but a low positional order. This means that it's not like a solid crystalline where there's a high order positional order. So they align parallelly, but they don't have fixed positions. So they're fluid, but very viscous in general. And something very useful, which we're introducing before, is that they have the electric anisotropy. The electric anisotropy basically means that depending on the orientation of the molecule, the either permittivity or refractive index, also because it shows this anisotropy in those situations, changes. So here we have a parallel permittivity and a perpendicular permittivity. This means that if we're able to rotate this molecules, such as, I'm going to explain this in a bit, we're able to tune which refractive index our electromagnetic wave C, in a way, the refractive index, the permittivity, well, also the refractive index, the permittivity that our electromagnetic wave C, and thus tune where our resonance is. Here we see the molecules fully relaxed, so, and at an horizontal plane, and no matter if our electromagnetic wave varies vertically or horizontally, both of them in a way see the perpendicular. So here we would have the same for both polarizations. But if we manage to have our molecules in the vertical position, we're able to have for one of the polarizations. So if our electromagnetic field is changing in this direction, we now have a different permittivity. in a way can tune can shift where the resonance is. And then there's also intermediate states where, since the molecule is not aligned with any of them, we have kind of an effective permittivity. It's not really an effective permittivity. It's a tensor where you can extract exactly what permittivities it interacts with, but more or less you can approximate it with an effective permittivity, which is within the bounds of both the parallel and the perpendicular permittivity. And liquid crystal has another great thing, that it also has anisotropy at low frequency biasing fields. So at AC frequencies, if we connect it to the network, it also interacts with it differently. So by applying a field at low frequencies to our liquid crystal cells that we usually call, and by varying the RMS voltage, because it doesn't react to the polarity of the field, we can tune the orientation of these molecules. Here's a more approximate situation of what happens, because we cannot fully change all of them in bigger cavities, but basically by changing the voltage we apply, or the RMS voltage that we apply, we're able to rotate our structures. This means, again, going back to the previous slide, that we can tune the permittivity that our electromagnetic wave is seeing. And this in itself, well, would allow us, with the exact same geometrical setup, just by changing the voltage that we apply, we can generate, as we can see here, different phases. We have the exact same geometry, but we have the two resonances, and well, this is phase, and just by changing the voltage we're applying, we can shift in a way where laterally where the resonances would appear, and that we can achieve at any specific frequency. Here in the red arrow, we can achieve a whole range of phases that allows us, once again, to generate whatever phase profile that we want. In reality, it is not as simple as the picture before, because we need to do several things for the liquid crystal to work. First, we need to provide it a cavity, which we usually do by having two substrates. They can be different materials, but they're generally going to be covered, but it can be like glass and quartz substrates to create the cavity for a liquid crystal to not escape, because if not, it's just going to flow everywhere, so not very useful. And we still have to have the backplane, which we usually use gold, but we have to have a ground backplane for reflection to happen, because if we don't have a backplane, it would be in transmission. And we have to introduce our dipoles. So here we have, in this example, we have 3 dipoles to achieve the resonances. Then, since we have to apply electric field in between the ground plane and the dipoles for liquid crystal to rotate, for its molecules to realign in the different directions, we need to add biasing lines, which you can see here, here, and here, to get our electric signals to the specific places. This means, in a way, that these biasing lines and all the things we end up adding, this also changes the natural frequency of our system. So we have to fine tune it in a bit to achieve still our resonances that we can use. But by doing this and by changing within different voltages, here we have the two extreme states. So when we don't apply any electric field, and when we apply over the top, over saturation electric field, we can see that we're shifting our resonances in amplitude, and in phase, we see that at certain at any frequency, we have a change in the phase delay levels that we can achieve. This entails that we can create basically any phase profile that we want, in a way. We can, since we're able to generate just by tuning the voltage, the different phase delays, we can create any kind of phase pattern or phase mask that we might call to achieve gratings, prisms, lenses, reflectors. As long as it has a phase pattern, we can, in a way, generate it. And this is a bit of the introduction. Well, this is a bit of the talk. If you want, sorry. If you have more questions on manufacturing and things like that, because we manufacture in-house, we also measure in-house and things like that, I can explain. I have a couple slides afterwards, but this is a bit of what I do, or what we do in my two groups. So yeah.
So are there any questions for the public?
Hi, thank you for interesting talk, especially because of the very thorough introduction to theory. Could you extend a little bit more on the materials are being investigated for the liquid
Crystals?
crystals.
Yeah.
themselves?
I'm not specialized in the materials. I just use them, and nor is my group specialized on the chemistry part of the materials. If they're complex, maybe Xavi might answer better, though I'm not very sure he knows the better. There's people that do research specifically on materials. I know they're polar molecules that does align, but there's many different types. Within the liquid crystal reflector arrays, we tend to use pneumatic liquid crystals, which are the rod-like that align to the module or to the absolute value of the electric field, but I'm not so much of an expert within liquid crystal. I know there's plenty of them, and I can name several of them, but I'm not sure that's useful as for explaining more on how they behave internally. If you have more questions, one of the other professors on liquid crystals might know a bit more, but he's in the US right now, so I'm not sure if he'll be able to answer it.
Have you already thought about future application?
Yes, here I explained just the basics of how it works. But reflector arrays, it's a field that has a wide range of applications and development in passive reflector arrays, which is what I explained before with just changing the geometrical profile. You can still achieve this phase variation. So in passive reflector arrays, where you generate a surface, would you pre-calculate which phase delay you need on each of the different cells of the matrix you have? There's a lot of things being developed. So right now, in general, we're trying to see what we can reproduce with this technology, because the losses you have, well, the materials you use as a substrate for this and the losses they imply are way lower. Here we have several dBs of losses, up to 9, 10, depending a bit on the material that they're using. But in passive reflector arrays, they might have 0.1 dBs of losses. So it means that their performance in many different things, it's better and or easier to fine tune. Whereas with liquid crystals, since first of all, actually you might have heard liquid crystal from liquid crystal displays, which is LCDs, the typical displays that there have been the displays we use for computers. They're optimized at optical frequencies, which means that the losses, the performance and everything is optimized for optical frequency. So adapting them to RF, it's not as easy. There's some commercial liquid crystals for RF, but they still do not perform as good as passive reflector arrays. The good thing is that you can change from this phase pattern to this phase pattern just by changing the voltage. So you can, with one reflector array, theoretically do whatever in a way. So not only seeing how they work in loss situation, in time of rotation, because it takes time for the molecules to rotate and things like that, but also in, okay, we want to do it for both polarizations, since I was explaining here before, two polarizations of the field, two orthogonal polarizations or circular polarization of the field, seeing how we can make them work for different polarizations, for different applications, for beam steering, not only in one direction, as we see here, where you have a change based along this direction, but maybe changing along this direction. Because I didn't go in depth into all the things we are going through, because I think it was like, okay, first understand this before going into the specifics of the thing. But there's definitely plenty of things, or way too many things for me to do research on. There's for sure.
Okay, if there is no more questions, Pablo, thank you again. And thank you all.